Kinetic energy is the energy an object has due to its movement. It's positive and scalar. Examples are mechanical, electrical, due to the movement of electrons which carry the electric charge, and thermal. We can work out kinetic energy of this car that's moving at 18 meters per second and has a mass of 800 kilograms. We use the formula half mass times velocity squared. Potential energy is stored energy possessed by an object due to its position or arrangement of its component parts. This could be elastic, chemical, or nuclear. In this example, we look at gravitational potential energy. A car is stationary on a 200-meter high ledge. The formula for gravitational potential energy is mass times gravitational field strength times height. If the car drives off the ledge, some of this potential energy is converted to kinetic energy. It still has height, so it will have potential energy too. Due to the conservation of energy, we know that energy cannot be gained or lost, only converted, so potential energy plus kinetic energy is constant throughout the fall. In other words, kinetic energy gained will be equal to gravitational energy lost. Elastic forces. Tensile stress is when a force is applied to an area to cause deformation. It is measured in newtons per square meter, or pascals, and is calculated by force acting divided by area. Strain is how much the material has stretched, which is calculated by change in length divided by original length. Strain has no units, as it's a ratio between extension and original length. If we remove this stress, the area either is permanently distorted, plastic deformation, or it returns to its original shape, elastic deformation. Young's modulus calculates the stiffness of a material, i.e. how much the material will deform under stress. I should note, tensile stress can be written as a sigma and tensile strain with an epsilon. Young's modulus is stress divided by strain. It can be observed in the gradient of the line. Hooke's law states that force applied is directly proportional to extension when environmental conditions are kept constant. It can be calculated: force equals constant, for example a spring constant, times by extension. The area under a force extension graph shows the work done to deform the material. This work done, or energy stored, can be calculated half force times change in length. Limit of proportionality is when Hooke's law no longer applies. It can coincide with elastic limit, which is the maximum load the material can take and return to its original size. When the internal structure of a material being stretched changes, the yield point is reached, and it's beyond the elastic limit, so it shows plastic behavior. Materials can be brittle, they cannot be permanently stretched and break soon after the elastic limit, and ductile, where they become permanently stretched. All objects have gravitational fields around them, however most of the time it's too weak to notice. You do notice when the mass of an object is really large, let's say the Earth. There is a strong enough attractive force that we are held on the ground instead of floating in the air or bouncing like on the moon. Newton's law of gravitation states, all masses attract each other with a force that is proportional to the product of their masses, and inversely proportional to the distance between the centre of the masses squared. We can arrange the formula gravitational constant, calculated at 6.67 times 10 to the power of minus 11 Newton meters per kilogram squared, times by the product of the masses divided by the distance between the centre of masses squared. Inverse square law. A light is set up with a board in front at a distance of r, in which the light covers the entire board and not past it. If the board is moved to 2r, the light will cover 4 times the size of the first board. If we move to 3r, the light will cover 9 times the first board, with intensity reduced by 9 times. This means the intensity of light is inversely proportional to the distance from the torch. Physical properties are reduced as distance increases, for example gravity. Intensity decreases as area increases. Non-conservative forces. Mechanical energy is not conserved and instead is often converted to other forms of energy. Energy is either removed or added to a system. Work done depends on the path taken. Examples are friction, air resistance, and tension. If we move this plane from A to B on a winding route, air resistance will be higher than if you go directly from A to B. This is because the plane will come into more contact with air molecules and therefore more friction. So more kinetic energy will be converted to thermal. This energy dissipates to the environment, so cannot be fully converted back to work in the system. In a car, we use friction to slow down. Brake fluid under high pressure moves a piston that's connected to the brake pads that then makes contact with the rotor disc. The bumpy surfaces of the material slide past each other and cause kinetic energy to convert to thermal energy, reducing the kinetic energy. Conservative forces. When work is done, conservative energy systems do not depend on the path taken. Energy does not leave the system. It's associated with potential energy and kinetic energy. Gravitational energy system example. Let's say we have a 16 kilogram crate that is lifted 8 meters. The energy to lift equals 1255.68 joules. This is going to be negative as we are lifting against gravity. If this box is moved horizontally along the same height, there will be no change in gravitational potential energy. If we move the box back to the ground, the gravitational potential energy will be plus 1255.68 joules to equal 0. So this elevation and depression will result in 0 joules. So no work overall will be done from point A to point B. Elastic energy system example. If we take a spring with a known constant and draw a line where the spring rest position is, its equilibrium, and extend it past the rest point, x, it will gain elastic potential energy. If this same spring is extended by 2x, the potential energy will increase by twice as much. When the spring is released, the potential energy will return to kinetic energy as the spring returns to equilibrium. Due to the energy being conserved, the potential energy and kinetic energy will be equal. Energy is not dissipated to the surroundings.